Well, we need to address quantum mechanics, and the reason that we need to address quantum mechanics is I want to explain to you eventually how the distribution of matter is dispersed throughout the universe and why it is dispersed in that matter. And it's going to take a little bit of background on quantum mechanics. Now, in this particular slide, you're looking at the pioneers of quantum mechanics in the early part of the 20th century. And it's Niels Bohr, Max Planck, James Chadwick, Ernest Rutherford, probably people that you've already heard about. We can use the Newtonian mechanics to get to the moon. So we don't have to start worrying about some of these details of quantum mechanics until we deal with subatomic particles. And so, and that's what we're going to have to be kind of dealing with here in the early part of the universe. A strange place where all of the subatomic particles were behaving in strange ways, and we had some variations that can only be explained apparently through quantum mechanics. So let me go on with explaining to you the two great discoveries in quantum mechanics, or related to quantum mechanics, that were made in the last century. And a lot of people don't realize it, but these discoveries made by Heisenberg and Schrödinger were probably something equivalent to general relativity. We don't hear about what Heisenberg and Schrödinger did as much as we do about Einstein and general relativity, but I think they're probably just as important in understanding the world we live in. At the subatomic particle level, the world is just plain strange. And Feynman, who won a Nobel Prize, worked on quantum mechanics. To paraphrase, he said, you just can't understand it. Don't even try. So obviously, we want to try to understand it, but I want to emphasize that if you're going to ask why is it this way, that there's just no way to explain it. It's kind of like asking why are we here or something like that. Well, this is a slide of Heisenberg. Now Heisenberg is up here. That's Werner Heisenberg. You may know Heisenberg if you've been watching Breaking Bad, but I'm here to tell you that the guy with the black hat on is not the real Heisenberg. He named himself after Werner Heisenberg. And Heisenberg discovered the uncertainty principle. Now, the uncertainty principle on the surface doesn't sound like such a great discovery. All Heisenberg said was, look, we can never know when we're dealing with pairs of particles, subatomic particles, we can never know the position and the momentum, that is the mass times the volume, at the same time. It doesn't sound like a big deal. If you look at the microscope here, if a photon comes in and it hits an electron, well, it's common sense that electron is going to be moved by the photon coming in. That's a little different than if you're looking at a block of ice under there, because a photon isn't going to move the block of ice. So that's where it starts to become a little strange. By the time that photon gets up the microscope to our eye, well, that electron has moved on. So we might know something about the position when the photon hit it, but we can't know the position when we're seeing it, because it's been affected by the mere observation. And this is the key. We're discovering that observation has an effect on the physics, on this weird thing called quantum mechanics. And it's kind of, I think you can put things in perspective if you think about how people thought in the 19th century. 19th century physicists said, hey, let's kick our feet up here. If we can determine the velocity and the speed of all the particles in the room, then we can predict the future in that room. Well, that's not possible, because we can't know the position or the velocity and mass at the same time. So it has tremendous ramifications on our ability to predict the future. In fact, we can't predict the future because everything is based on probability. Now let's deal with that idea of probability a little bit more, because that's where Erwin Schrödinger comes into play. Here's a picture of Schrodinger, again working in the 1930s, early part of the last century. The popular view at the time of how the electron moves around the atom was it was in one position and it revolved much the same way a planet revolves around the sun. But Schrodinger realized from Heisenberg's uncertainty principle that we had to predict where the electron was on the basis of probability. So he came up with a series of equations which actually, as you can see in the diagram here of the s orbital of the hydrogen atom, that were most likely, the dots show you where we're most likely to find it. So where you have a concentration of dots, blue dots, it's going to be concentrated in that area. Where you have less, then you're less likely to find the electron. So we can see that we're going to most likely find it closer to the nucleus than farther away. And it's all based on these probability equations. Let me show you start to show you anyway, how bizarre this is. This goes back to 1801 with Thomas Young. He did something called the two-slit experiment. Now, it's just common sense what he saw when he had one slit open. If you look at the graph above the electron gun, by the way, the electron gun generates just what it says it does. It generates electrons and they go out. And if you close one of the slits on the right, say we close the right slit and we just let electrons go through the left slit, then if you come up on the diagram up here at the top, you'll see the distribution of electrons if we do that enough. And you can see it's pretty much a bell-shaped curve. You get most of the distribution in the center, and as you go away from the center, you get less and less electrons striking. The same thing is true if we opened up the right slit and closed the left slit, you'd get the distribution that you see on the right. So doesn't it make common sense that if you open both slits, that you would get a combination of the pattern that you see, left and right? And it turns out that is not the way it is at all. If we just look at one slit, we see, or one electron going through a slit, and we know which slit it went through, you'll see that it'll show up. In this case, it went through the right slit here in the individual electron. But then if you start accumulating electrons, you can see that it's very strange, at least it's strange compared to what we might expect. You're getting a swath of concentrated strikes with electrons, then you're getting an area where no electron strikes, and then another swath, and then an empty area. So, and it's going out on both sides this way. So it's bizarre because it's not what we expect. And Young realized at the time, he suggested that maybe this was a wave interference pattern. And then this puzzled everyone because everyone said, how the heck could a particle be behaving like a wave? And so we begin this odyssey of trying to understand subatomic particles and how they behave. Now, I want to show you a video here as to how we would get a wave pattern going through these two slits when they're open. They go through and interfere, and that's the key, that they interfere. Where the peaks and troughs of the waves hit, they'll cancel each other out, as you can see, but where the waves and the crests interfere, you'll get what we call constructive interference. You know, just as an aside, I like to keep things in the real world sometimes here. I don't know if you've heard about rogue waves, but we can have storms in the ocean that are quite I mean, hundreds of kilometers away from each other, and the waves generated from those storms they'll move out from the center of those storms, and sometimes they'll interfere with each other in a constructive way, and the waves will get bigger, and then they'll run into another storm, and maybe the wave will construct with another wave, and then you can build up these so-called rogue waves, and we have some history of these rogue waves striking cruise ships and damaging them, or even swamping vessels or sinking them at sea. Now, I don't want you to think that every time you go in the ocean you're going to be potentially hit by a rogue wave. They're extremely rare. We cannot observe the electron behaving both as a particle and as a wave in the diagram that I just show you. So if we learn which slit the electron passes when both slits are open, we lose the diffraction pattern. And that's the crazy thing about this. Here it is again. It's an observation that we're making that seems to affect the way the electron behaves. And that's the crazy way, or the crazy world of subatomic particles. In fact, Schrödinger wanted to convey to everyone just how weird this world was. So he came up with a thought experiment. It's now referred to as Schrödinger's cat. What it postulates is that if we put a cat in a box and we have a radioactive source that generates decay of an atom, say an isotope, say once an hour on average, then we would expect maybe an electron or a subatomic particle to come out of there through the decay, and it would strike then the lever box, and when it strikes it, it would cause a hammer to fall and break open a flask full of poisonous gas, and that gas would go out and kill the cat. Now, the idea here is that if the electron behaves as a particle, then it'll force the hammer, or it'll allow the hammer to break the flask. But if it's behaving as a wave, well, it can't affect the button, so to speak, on the side, and the lever won't drop, the hammer won't fall, and as a consequence, you won't kill the cat. So here's the weird, spooky idea about subatomic particles in quantum mechanics, and that is that Schrödinger said we don't know whether the cat is alive or dead until we look in the box and we force nature, if you will, to decide whether the electron behaved as a wave or as an electron. The point Schrödinger was trying to make is basically correct, that we have to look. So in a way, the cat's in some sort of suspended animation, so to speak. He's neither dead nor alive until we look. So it's really, really bizarre. Now, let's try to get back to the whole reason that I'm talking about quantum mechanics, and that's from some data that was picked up by a whole series of satellites. Remember now, in the early universe, we had protons, neutrons, particles flying around. We had photons, and those photons, it turns out that there were 1 billion photons for every particle that existed. Now, we think that part of this was due to matter and antimatter interaction, which produced energy, which in turn produced the photons. So for whatever reason, we had one particle in 1 billion that survived that interaction of matter and antimatter and created this energy. Now, this drives physicists crazy because they're asking themselves, why would we have more matter than antimatter? And this is one of the great mysteries in science. We don't know the answer, and as I've told you before, when science doesn't know, we're going to tell you that we don't know. Now, there is some thinking that maybe inflation caused the matter and antiparticles to be separated and spread out, and we have antimatter out there in space. But there's really not a whole lot of evidence for that. So we must have had some asymmetrical creation of matter over antimatter, which is just speculation. In the early universe, the photons were constantly striking these neutrons and protons, and so the photons can't travel in a straight line. And so I want you to think of it as just one great big mass of fog. We can't see through this. It is like a fog out there. The photons are bouncing around. They can't fly off into space freely, so we have a fog. So when we look back to about 380,000 years after the Big Bang, there's this big wall or bank of fog that exists out there. And as far as anybody knows, we'll never be able to see beyond that fog. So any galaxies that form, and we've seen them almost back to that fog, so we know that they started to form very early in the universe, at least 380,000 years after the universe was formed. We probably had galaxies forming. So the big question is, why do we have galaxies forming if this energy and mass was evenly distributed across the universe? And that's where we get back to this idea that it wasn't evenly distributed. And then you have the question, well, why wasn't it evenly distributed? And that goes back to quantum mechanics. But I want to emphasize that 380,000 years ago, we probably, atoms were created, and that allowed photons to travel without running into particles that would deflect them and keep them all in this fog. And so the universe kind of clears at that point, and we can start to see things that are happening. Now this map of the Planck cosmic microwave background radiation was the last, or the most recent satellite that went up and collected data. But in the late 1990s, we had a satellite called COBE, and that went out and measured the cosmic background radiation, and it was the first one that discovered slight variations in the cosmic microwave background radiation. Now, I know it doesn't look like it in this diagram, but the background radiation is incredibly smooth. It's smoother than a billiard ball. So just try to think about trying to find variations on the surface of a billiard ball, and then multiply that by some factor of more difficulty. That's what we've got with the cosmic microwave background radiation, and the COBE team had to work with the data, and I remember the word finally came out that they did find some variations. Scientists were worried when they weren't discovering any variations in that background radiation, because the Big Bang predicts that we will find those variations. And it was very exciting at the time, because finally they discovered that there were variations that were predicted by the Big Bang, which was, by the way, a big support for the Big Bang, as you'll see in just a minute in a slide I'm going to show you. And the idea is that because of quantum mechanics, we should have random fluctuations in the energy. I want to remind you of something I've talked about in the past, and that's a perfect vacuum. If you remember, a perfect vacuum isn't a perfect vacuum. They're these so-called virtual particles that appear, and then antimatter and matter, and they destroy one another, and you're left with energy. So the vacuum, and they're random. They start to appear randomly, and with this background radiation, we have these random fluctuations that we see, and they're very tiny. But, and here's the key, they were big enough to where when the photons could be released out into space, and the way that mass and energy was behaving, it was the same prior to that. And then the release of the photons allowed them to disperse. We started having matter beginning to clump together because of these random fluctuations, clumping together in such a way that we could begin to form galaxies. And I'll come back to that. I did want to show you one graph here before I go on, and that is that this is a graph of the spectra from the cosmic microwave background radiation. Now, believe it or not, there are two curves. One of the curves is the theory of what the spectra looked like before we went out and we looked at it. And then the other is the curve that we actually measured from the background radiation. And they fall on top of one another precisely. So this is amazingly compelling evidence for the Big Bang. Here we have a case where theory predicted something, and we went out and we observed it. I mean, that's the essence of science, really. And here's George Smoot up here on the left. He was the head of the COBE team that went out and measured the first variations in the cosmic microwave background radiation, and he won the Nobel Prize 2006. We've had several other satellites since that time. YMAP has gone up and measured it, and then the Europeans put up the Planck satellite. I've talked about black body radiation in the past. Well, if you have an opaque black body, it's going to give off a very constant amount of radiation if you heat it up. And so that's what we refer to as black body radiation. And that's true of the cosmic microwave background radiation. It has a very specific amount of radiation that's coming off at each wavelength, and we can measure that very precisely. And it turns out to be 2.725 degrees Kelvin. So it's very cold, and that's because as the universe has expanded since the Big Bang, we've had the energy spread out through space. The temperature has gone down, it's been lowered, and now it exists out there as this very low 2.7 degrees Kelvin temperature. But it's out there. It represents the energy left over from the Big Bang. It also represents how mass was distributed in the early Big Bang, because energy and mass were together and behaving the same in the great temperatures of the early Big Bang. So we can look and get an idea of what the mass looked like in its distribution with these small quantum fluctuations way back in the early part of the universe. And so that allows us to go out and understand now the way data is distributed throughout space. What you're looking at here is the 2D galaxy redshift survey. Every one of those blue dots there is a galaxy in our space. It was done by the Anglo-Australian Observatory between 1997 and 2002. And it goes back out into space for about 2 billion years. Since that time, we've had other surveys which have taken us to virtually the edge of space, and it all looks pretty much the way this does. Very precise measurements and a large quantity of galaxies to look at. And you can see, I hope, that this doesn't look anything like the cosmic microwave background radiation. And that's because when the photons flew off and mass and energy were separated, we have this thing called gravity that affected mass but didn't affect energy. And so the mass, including the dark matter, which helped, by the way, that dark matter that exists out there helped. It has gravitational traction on it because it's mass, and it helped in bringing in this matter. So in those areas where you have slight concentrations of energy, we also assume that there were slight concentrations of mass, and that mass, when it got concentrated, it was able to, gravitational effects were able to take over, and it started bringing the mass together, and we started then clumping mass together. Once you start clumping mass together, that means that the hydrogen and helium can start to form stars, and you can begin to form galaxies, and so on and so forth, and that's how we think that the galaxies got formed. I've got this nice little video to show you here. If we start out with the perceived or the measured quantum fluctuations that we see in the background radiation, and we disperse mass in the same way, this video is showing how you can get a pattern that looks very similar using gravity, how you can get a pattern that looks very similar to what we see out there right now. So I think a case where modeling of known physical characteristics of our universe can generate what we see. And I think that's important. So gravity kind of offsets this matter thing from energy and makes the difference and forms the galaxies. And fortunately for us, gives us a place to live. If we didn't have these fluctuations, then we wouldn't have humans. The matter in space would be just evenly distributed with no condensation, if you will, of galaxies.